All right, so we are taking a look at the class data. This is from 5th period and 1st period class data. So it's going to change a little bit over the day as we add in that additional data, but I don't expect it to change a whole lot. So your plotted graph should look something like this, where you have kind of 4 distinct trend lines. And what we're going to try to make sense of would be, what are those trend lines telling us, first of all? And what conclusions can we make about each of these materials that we were studying? So let's start with the steepest line. Your plot for steel should have been the steepest, hopefully. And one of the things that we have here in Google Sheets in the graph is some statistical information about that line of best fit. So I want to explain what that is showing. So for steel, we've got this is actually writing out the formula for the line of best fit in linear form. So you can think of this as y equals 7.32 times x plus a very small negative number, okay? And what it's doing really is writing out the trend line equation in the form y equals mx plus b. And what we're most concerned with in this graph is the m term, which is the slope. So for steel, I'm kind of zooming in and thinking about this 7.3 number. So hopefully when you calculated your slopes, you're somewhere around 7. You might be at 6. You might be at 8. But hopefully your slope with your individual data and your trend line was near 7. So if I would rewrite this whole equation, not in terms of y and x, but in terms of what I'm actually plotting here, the y-axis is mass. So it's really saying mass equals 7.32. And I'm going to say, let's just go with 2 significant digits to give us kind of a more round number. So I'm going to round 7.32 to 7.3. And the units on the slope would be rise units over run units. So it's grams per cubic centimeter. That's my slope. Times x. Well, the x variable here is volume. And if I truly believe the trend line should trend through 0, which I do because 0 volume would mean 0 mass, I just ignore the intercept. It's a very small number anyway. So this is what I would call the mathematical model or equation that describes our relationship between mass and volume for steel. So I'll ask you guys, what is this actually telling me about steel? To say that the slope of this graph is 7.3 grams per cubic centimeter. Anybody have an idea? It has a name, but more importantly than the name, what is it like telling us conceptually about steel, or at least the type of steel that we had in this investigation? Thoughts? All right, let me give you a hint. It's grams over, so grams per cubic centimeter. We've got our little cubic centimeter piece, right? It's the volume unit that we're using. If I would take a piece of the steel that we studied and cut a piece this big, we would expect it to have a mass of about 7.3 grams. It's telling me the mass per unit for steel, at least the steel that we studied, okay? So the word for that, I know you've heard it, is density. The slope in all of these graphs should be the density of the material. That's why I wanted you guys to estimate it. Slope equals density. So one of the things about chemistry labs that might be different from other labs that you do is the data is really important, right? You notice there were some groups that had calculated or measured something wrong. It was really throwing off our trend lines. So that's something that I think some students come in and labs are like fun. I do hope they're fun, but they're also really data driven in chemistry. So if you take bad measurements or you make a mistake or you write something down wrong, it really makes things confusing. So that's something just to consider kind of going forward. We really, really want to make sure that we're getting good data. So what that tells me is I can jot down the slope of these other lines, and that's telling me the density of each of those materials. So I'm going to go ahead and jot down 7.3 grams per cubic centimeter by my plot for steel. If I look at the aluminum data, again, I'm focusing in on the M term here. 2.7, I'm going to round it again to 2 digits. So 2.7 grams per cubic centimeter is my density of aluminum based on my data. Water, here's the slope. If I want to keep 2 significant digits, I would want to keep these 2, but I've got to round up. So really what it's saying for water is the density is 1.0 grams per cubic centimeter, which we expect to be true if we have good data. In fact, that's how grams was first defined. This much water, a cubic centimeter or a milliliter of water, has a mass of 1 gram. At a specific temperature, it can vary a little bit depending on what temperature you're at, but essentially we expect it to be 1. And then for wood, I'm going to write it as 0.43 grams per cubic centimeter. So the wood that we studied was the least dense. And so hopefully your lines of best fit from your group are pretty close to these. If they're drastically different, again, there's probably something up in your data that we need to get fixed. Okay. So one of the other things we like to do in chemistry is kind of judge our results, like how well did we do compared to the actual value. So let me just open up a tab. I'm going to start with aluminum because I'll tell you guys that was our best result so far. If I just Google density of aluminum, you guys got it. Okay, it is 2.7 grams per cubic centimeter. So that is right on the dot what we would want. That means as a group, we have great data. Our average values come out right on what we would expect. So you guys are to be commended for that. What I would say on that one is we have 0% error. There is no error. We're right on the expectation. So that's great. And notice our data points are really well clustered around that line of best fit. There's one little outlier here, but for the most part, it looks like we have really solid data. For water, water is supposed to be 1 as well. So good job, 0% error. Now, if you do have error, we'll talk about how to calculate it. Basically, you look at how far was I from the actual value divided by the actual value and then express it as a percent. We're always looking for 5% error or less in the labs that we do. That's a really good result. 10% error or less is okay, not quite as good. We really don't want to be over 10% error. If we're getting above 10% error, that probably means something's wrong with our data. Now, I can't do that for wood or steel. Wood and steel are not pure substances. There's not just one type of steel. Steel is a mixture of mostly iron and then other elements that are mixed in with it to help it have the properties that they want for a certain job. So steel that might be used for building construction has a different recipe than steel to maybe make a car frame or something like that. But we can get an idea, again, go ahead and just Google it, see if we're in the ballpark. So let's do density of steel. And we get a range. So this says a range between 7.75 and 8.05. And again, it's not going to be an exact number. Steel is not a pure substance. Steel is not on the periodic table. It is not an element. It is a mixture. So again, I'm thinking that's pretty good, right? We're around 7. It said 7 or 8 is what we would expect. Wood is the same way, right? Different trees have different densities. Wood derived from different trees tends to have different densities. Dry wood that's been dried out in an oven is going to have less density than like freshly cut wood because it's going to have a lot of water in it. So again, we can't really do a percent error for wood because it varies. But same idea. If I do a quick Google search, I'll do density of wood in grams per cubic centimeter. I'll actually go to this site. And you can see the different types of wood have different densities. The thing that we see that is in common for all of these is that they're all less than 1. Okay, and it varies quite a bit. Balsa wood is very, very low density. You can see that some of these other ones are more dense. And if you've ever done any woodworking, you know that's true based on like how easy it is to cut, how heavy it feels when you pick it up. I'm not actually sure which type of wood our pieces were made of. It might have been birch. I'm not sure. But 0.4 is the value that we typically get for wood.